In this video, we're taking a look at determining whether a function is increasing and decreasing based on the derivative, and then also something called the first derivative test. So we've talked about this a little bit previously, but if we're looking to determine whether a function is increasing or decreasing, and we're told that our function f is continuous and differentiable, continuous on this closed interval and differentiable on the open interval with the same endpoints, then we can say if the derivative is positive, then we can say that our original function f would be increasing on that interval. If the derivative is negative, then our function f would be decreasing on that interval. And then similarly, if our function is equal to 0 for some interval, right, for some interval inside the interval AB, then we would say that f is constant. So you can see that kind of illustrated here. So we have our function is decreasing from 0 up until this x equals a. And during that time, the derivative is negative, right? So all of the slopes of our tangent lines would be negative if we were going to draw them over that entire interval. And then on the interval from a to b here, we can see that it's just a horizontal line. So the slope of my tangent line would be 0. So it's constant. And then in this section here, my function is increasing, and we can see that the derivative, right, the slope of our tangent line would be positive on that entire interval there. And so this is going to hold. Now, one thing to note, it says for all x in the interval, so the derivative is positive for all x or it's negative for all x. There are some cases where we can say that our function is increasing where it has like singular points where it's equal to 0, right? So an example would be something like a cubic function. So this cubic function is increasing everywhere, even though here we have this critical point where we have a horizontal tangent. Because it's just a singular point in the interval, we basically just ignore where we have like singular points of horizontal tangents within our interval. If it continues to increase on either side of that point where we have a horizontal tangent, then we would say that it's still increasing. Or if it continues to decrease around that point, we'd say it would still be decreasing. Okay, so just keep that in mind. If you have something where you have a horizontal tangent and on either side of the tangent it continues to increase or decrease, then we continue to say that it's increasing over that whole interval. In this example, we want to determine where this function f of x equals x squared is increasing and decreasing. Now, if you recall from pre-calculus, you probably have a pretty good sense of where it's already increasing and decreasing. We know the curve kind of looks like this, right? It's a parabola. It opens up. And to the left of its vertex, it's going to be decreasing. And to the right of its vertex, it will be increasing. But we need to verify that result through calculus. So the first thing we want to do is take the derivative. So the derivative of f is going to be 2x. And we want to know where the derivative is positive and where the derivative is negative. Because when it is positive, that tells us that our function is increasing. Where it's negative, that tells us our function is decreasing. So to figure out that value where it's the values where it's increasing or decreasing, we first have to figure out where it equals 0. So you're going to set your derivative equal to 0, and we find that this happens at x equals 0. And we know that the only way that we can have a sign change, right, it can go from positive to negative, since it's a continuous function. I know it's continuous because it's a parabola. The only way that we get a sign change is if we have an x-intercept. So that's why we're trying to figure out where this is equal to 0. So this x-intercept basically splits our domain into intervals. And so it's going to be the interval to the left of 0 and then the interval to the right of 0. So the interval to the left of 0 goes from negative infinity to 0. The interval to the right of 0 goes from 0 to infinity. Now, because this is the only x-intercept, all values on this interval will be the same sign. All values on this interval will be the same sign. So we can pick any value we want to just test and determine the sign of our derivative. So I'll just use -1 here, and I'll use +1 here. So if I plug -1 into my derivative, I'm going to get a negative number. I actually don't even care about its value. I just won't care about the sign. And if I plug +1 in here, I get a positive number. So if you recall, we said when the derivative is negative, that tells me that my graph of f is decreasing. So A negative derivative tells me that f is decreasing. A positive derivative tells me that f is increasing. Now, when you are trying to determine intervals of increasing and decreasing, this chart is not sufficient in answering the question. You need to summarize your results and say it decreases on the interval from negative infinity to 0, and it increases on the interval from 0 to infinity. Just using the chart is not sufficient. You need to summarize your results. Part B. Again, we have a cubic function, so it is, again, a continuous and differentiable function on the entire real number line. So we want to figure out where is this going to be equal to 0 so that we can determine our intervals and test our points. So we're going to, well, we want to know where the derivative is 0, sorry. Right, so what is the derivative? F prime of x is going to equal 6x squared minus 12. So we can set this equal to 0, and we're going to get 6x squared minus 12 equals 0. If we want to solve this, we're going to get x squared equals 2, right? So you add 12 and divide by 6. Taking the square root of both sides, we're going to get that x is going to equal plus or minus square root of 2. So square root of 2 are the two places that we get x-intercepts in the derivative. So they're the two places that we could potentially have sign changes on either side of. Since this is defined everywhere, we're going to look from negative infinity up to the smallest number here, so negative rad 2. And then we have to consider the interval in between our two numbers here, right? Our two critical numbers, square root of 2 to square root of 2. And then from square root of 2 to infinity. Okay, so those are our three intervals here. Rad 2 is about 1.4, so if you want to pick a number bigger than 1.4 to test, here you can, so let's just do like 1.5. Or actually, let's just make it easy on ourselves and pick like 2. Here I can do negative 2, and a nice number in between negative rad 2 and rad 2 would be 0. So let's go ahead and plug these into our derivative to determine whether it's going to be positive or negative. So negative 2 squared is positive 4. 4 times 6 is 24. That gives me a positive number there. Plugging in 0, that makes that whole thing 0, and I get negative 12, so it's negative there. And then plugging in positive 2 also gives me 24 minus 12, which is going to be positive. So my graph, the graph of f, right, the graph of f, when the derivative is positive, f is increasing. So we see it's increasing there and there. And when the derivative is negative, the graph of f is decreasing. So again, we need to summarize our results. So we can say our function increases on the interval from negative infinity to negative rad 2, and then also from rad 2 to infinity, and it decreases in between those, so from negative rad 2 to rad 2. Okay? All right. So the first derivative test. The first derivative test looks very similar to, or we use the method that we were just doing to in the first derivative test. But what the first derivative test does is it helps us find local extrema. So we're trying to find relative maximum and minimum values, or local maximum and minimum values, using the first derivative test. So we say we let C be some critical number. So remember, a critical number is when f prime is equal to 0 or does not exist, right? So that's what a critical number is. And f is a continuous function on some open interval where it is containing our critical number. Okay. So the key to the first derivative test is there needs to be a sign change in our derivative. So if the derivative changes signs and it changes from positive to negative, so it changes from positive to negative, then we say that our function f, our original function, has a maximum, a local maximum. If the derivative changes signs and so if f prime changes signs from negative to positive, then we have a local minimum. If there's no sign change at C, right? So if there's no sign change at C, so f prime does not change sign, then there is no local extreme value. No local extreme value. So we can kind of take a look at what we have here in this diagram here. So we're on some open interval from A to B. You can see that at C sub 1, here at C sub 1, my derivative to the left is positive and my derivative to the right of my critical number is positive. So this derivative doesn't change signs, so we don't get a extreme value. But you can see here on the at C sub 2, right, we're changing from our derivative on the left here is positive and on the right is negative, so there's a sign change. And so we end up with a horizontal tangent and a local maximum, right? So we have a horizontal tangent here as well, but it goes from increasing to increasing, so there's no change of signs in our derivative, which means we don't have an extremum. So we're going to have a local max here. Because it's going from positive to negative, right? That means that we're going from increasing to decreasing. That gives us a local maximum. Here at C sub 3, we can see we're going from our derivative being negative to our derivative being positive. So it's going from decreasing to increasing, and that's going to give us our local minimum here. Now, at C sub 4, we don't have a horizontal tangent because this is not differentiable there. But notice that differentiability is not a requirement for the first derivative test. So we're looking at critical numbers, so our derivative is either 0 or does not exist. But you can see that to the left of our critical number, our derivative is greater than 0, and then to the right, it's less than 0, which makes this a... it says it's an absolute max, but remember, since it's in the interior of our interval, it is also a relative maximum. So it's also a relative maximum there. Now, one thing that is important to note in all of this, just because there's a sign change in your derivative does not guarantee that the value of C that you're looking at is going to be a maximum or a minimum. A key point in all of this is that our function f must be defined at C. And that's part of the continuity, right? If our function is not defined at that point C, then it's not continuous. And so therefore, that point cannot represent a maximum or minimum. So if our function is not defined there, not the derivative, but the function itself, if the function is not defined there, then we cannot have an extreme value. So if this was like an open circle here, this would not be a maximum or a minimum. But because it's closed, even though the derivative does not exist, it's a closed point and it's defined, so it does represent a maximum. Okay, so let's go ahead and use the first derivative test to find our local extreme values and then identify the intervals where our function increases and decreases. Okay. So to do that, we take the derivative. So what is f prime of x? F prime of x is going to be 3x squared minus 27. This is the same as 3 times x squared minus 9, which is 3 times x minus 3 times x plus 3. So this derivative is going to be equal to 0 at, so f prime of x equals 0 at x equals 3 and x equals negative 3. So these are our critical numbers. This is a cubic function, so it's never undefined. Its derivative is never undefined because this is a quadratic function. So the only critical numbers come from when our function's derivative is equal to 0, and they happen at x equals negative 3 and x equals positive 3. So if we lay out our intervals, it's going to go from negative infinity to negative 3, and then from negative 3 to positive 3, and then from 3 to infinity. Okay, so let's pick some numbers on those intervals, maybe negative 4, 0, positive 4, and test them. So I'm actually going to plug my numbers in -4, 0, and 4 into this version of the derivative, just because I think it's a little easier to see the signs of our numbers. So if I plug -4 in, so this 3 is positive. So if I plug -4 in here, that's going to give me a negative number. If I plug -4 in here, that's going to give me a negative number. A negative times a negative is positive. If I plug in 0, 0 minus 3, that's a negative number. If I plug in 0 there, it gives me a positive number. A negative times a positive is negative. And if I plug in a 4 here, that gives me a positive number there. I'm going to get a positive number there. Positive times positive is positive. Okay, so this here, we see that there is a sign change, right? A sign change in our derivative. So this is telling us that we're going to get some sort of maximum or minimum. So where do we have a maximum and where do we have a minimum? These are relative. Remember, these are relative. Relative maxima and minima. So the sign change occurs at the endpoints of our interval. So at x equals -3. So we have a maximum at -3, comma. And if we wanted to know the value of the maximum, we could just plug it in. For our case right now, I'm just going to say it happens at x equals -3. But again, like I said, you could find the coordinate by taking -3 and plugging it into f. And it goes from positive to negative, right? The derivative is going from positive to negative, so that tells us it's a maximum. Here at +3, my derivative is going from negative to positive, so that means we have our minimum. So we have a minimum at 3. So I could plug 3 in again and figure out what the value is, but I don't care too much about that right now. I just want to find the x values. So this is the relative maximum and minimum. Where is my function increasing and decreasing? Well, remember when the derivative is positive, that tells me my function increases. Where it's negative, that tells me it decreases. So it's increasing. So again, remember we need to summarize this. On the interval from -infinity to -3, and then also on the interval from 3 to infinity. And it decreases on the interval from -3 to 3. All right. In this example, again, we're trying to do the first derivative test. So I need to find the derivative of f. And we can use the product rule because it's two functions that are multiplying. So to find f prime, I'm going to use the product rule. So it's the first times the derivative of the second plus the second times the derivative of the first. Whoops, sorry, that's sloppy. Both of these have an e to the x in common, so I'm going to factor that out. And when I factor that out, I'm left with x squared minus 3. And then factoring it out from here, I get plus 2x. So let's go ahead and rewrite this in standard form. So we get e to the x times x squared plus 2x minus 3. This is actually factorable. So let's say that f prime of x is equal to e to the x times, this factors to be x plus 3 and x minus 1. All right, so now this is continuous everywhere. It's differentiable everywhere. We don't have anywhere that it is undefined. So let's go ahead and figure out where our function is equal to 0. So we do that by setting each piece equal to 0. E to the x actually never equals 0, so we're not going to get any critical numbers from this portion. X plus 3 equals 0 tells me that x equals -3. And then x minus 1 equaling 0 tells me that x is equal to 1. So we have two critical numbers at -3 and at 1, and those are going to determine our intervals. So split the number line at these values and set your intervals. So from -infinity to -3, and then again from -3 to 1, so in between our critical numbers, and then from 1 to infinity. So testing some numbers, so let's go -4, 0, 2. Let's go ahead and plug in. Now, one thing to note is e to the x e to the x is always positive. So this piece right here is always going to be positive. So we have a positive times, plugging in -4 is going to make that negative. Plugging in -4 is going to make that negative. So a negative times a negative is positive times positive is positive. So that means this is increasing here. Plugging in 0, again, this is going to be positive. And plugging in 0 here makes this a positive. Whoops. So 0 plus 3 is positive. 0 minus 1 is negative, though. So this whole thing is going to be negative, which tells me f is going to be decreasing there. And then the last piece, plugging in like 2, makes that positive, makes this positive, makes this positive. So all of those are positive, and we get a function that increases. Now, it seems like so far in all of our problems, we've gone positive, negative, or negative, positive, negative. That is not always going to be the case, so you do still need to do these tests. It is not always going to follow that same pattern, so don't fall into that trap. Make sure you're testing all of your intervals. Okay, so what does this tell me? So here, in this portion right here, I have a sign change from positive to negative. So at x equals -3, I go from positive to negative, which means I have a relative maximum at x equals -3. And then at 1, we go from negative to positive. So that tells me I have a relative minimum at x equals 1. Now I know that these are in fact maximum and minimum values because this function is defined everywhere. So these points do exist in our original function. And my function is increasing, increases on the interval from -infinity to -3 and from 1 to infinity. And then it decreases on the interval from -3 to 1. -3 to 1. Okay, one more example and then we will be done. So this one, there's actually a lot of intervals in this one, and you probably won't get as many as this, but I just wanted to kind of give you a sense of what you could experience. Okay, so this we're just asked to find relative extrema. We don't have to find or identify the intervals where it's increasing and decreasing, but we're still going to be using the first derivative test. So find the derivative. So f prime of x equals, this is a quotient rule situation. So let's go ahead and set up our quotient. So it's the denominator, x squared minus 1, times the derivative of the numerator, minus the numerator, times the derivative of the denominator, all divided by the denominator squared. Okay. So let's go ahead and like expand this a little bit. Let me clean this up here. Whoops. Whoops. Here we go. All right, so we want to distribute, so we're going to get 4x to the 5th minus 4x cubed. 4x to the 5th minus 4x cubed, and then minus 2x to the 5th. And then when we factor, if we factored x squared minus 1, it's going to be x plus 1 and x minus 1. And each of those terms is going to be squared, so it's x plus 1 squared, x minus 1 squared. We can clean this up still even more. Combining like terms, we're going to get 2x to the 5th, and those are going to have a common factor of 2x cubed, so I can factor that out. 2x cubed times x squared minus, right, because this is, I'm skipping steps, and I probably shouldn't. So we have 2x to the 5th minus 4x cubed over our denominator, which was x plus 1, x minus 1. Each of those is squared. Factoring out the common factor, 2x cubed, we get x squared minus 1, or sorry, minus 2. And then we have our x plus 1 squared and x minus 1 squared. Okay, that's our derivative. Now, the reason why I wanted it down into this form is because I need to find all my critical numbers. So what are my critical numbers? Critical numbers are when this is equal to 0 or when it's undefined. So it's not defined at -1 and +1. So x equals -1. X equals +1. That comes from my denominator. The numerator, when this 2x cubed is going to be 0 when x is equal to 0. So that's another critical number. And then solving x squared minus 2, if I were to solve this, I'm going to get that x is going to equal plus or minus the square root of 2. Whew. So we have a bunch of critical numbers. We need to break up our the domain of this into those different intervals. This is not defined everywhere, but it's defined everywhere except for -1 and 1. So all these other numbers are good as far as intervals are concerned. So we're going to go from -infinity. The smallest critical number is -rad2. Then we're going to go from -rad2 to -1. Then we're going to go from -1 to 0. We're going to go from 0 to +1. We're going to go from 1 to +rad2. And then we're going to go from rad2 to infinity. Remember, rad2 is about 1.4. So if I pick something like -2 here, maybe like -1.1. Here, maybe like -0.5. Maybe +0.5, +1.1. And then +2 there. Okay. Now, if we go through the process of checking all of these, right? Plugging in the negative, like plugging in these values back into f prime, what do we end up with? Well, we're going to end up with a negative on this interval, a positive on this interval, actually, again, a positive on that interval. Then we get a negative on this interval, a negative on this interval, and then a positive on that interval. So that tells me we're decreasing here. We are increasing, decreasing, decreasing, and increasing. Okay, which I actually didn't need that for this problem. I just needed to find the extrema. So remember, we look for relative extrema at sign changes. So here's a sign change in our derivative. It goes from negative to positive. So that means that at -rad2, we're going to have a relative minimum. A relative minimum at x equals -rad2. We get another, so here it goes positive, positive, so there's no sign change. But we get a sign change there. And then we have another sign change here. It goes from negative to positive at both of these places. So we have relative minimum at x equals rad2 and -rad2. And then here it goes from positive to negative. That gives me a relative maximum. Oh, that's sloppy, sorry. Maximum at x, at x equals 0. 0 is the number in between that interval. So those are where we have our relative extrema. Now, one thing that I want to say before we finish this video is, let's say hypothetically, right? Let's say hypothetically, here, this one here was actually negative, right? Let's say it was actually negative, which would mean we would have a sign change there. Would this represent a relative maximum going from positive to negative? Generally, we would say yes. However, this happens at x equals -1. Notice that if I plug -1 into my function is not defined at -1. So even though there's a sign change there, you have to check and make sure that the x coordinate or the x value where the sign change occurs is in the original domain. And since it is not, that would not represent a maximum.